All right, sound check, and also might as well check the video too and make sure that is working fine. Do I see my hand moving there, and do I hear myself? Yep, I do. Okay, headphones off. And let's finally get this show on the road. I had to postpone it twice. Those who were looking at the schedule probably noticed I postponed it by one day, and then on Monday yesterday I had to postpone it again, but here we are. I was thinking of just canceling this today even and just waiting until next Sunday, but I don't want to screw up the schedule too badly, so the show must go on. The compromise I'm making is that today I'm probably just going to be going for 2 hours instead of the usual 3. But we'll see how it goes. That is life. Busy, busy, busy. It also didn't help that the weather was not on everybody's side this weekend. So yeah, today we're finally starting a new chapter. I know some of you are excited because you are sick and tired of doing force. So let's talk more about force. Okay, today the plan is to discuss work and kinetic energy and how those two things are related. And we'll probably get around to doing some practice problems with those, and then I'm thinking next time will be potential energy and then just a bunch of problems, potential energy and mechanical energy and its conservation, and then a bunch of problems on that, and then the session after that will be a quick introduction to power, some problems involving power, which is not going to be much because power isn't really all that exciting in Physics 1. There's not that much that you can do with power, with the content of Physics 1 at least. It becomes a little bit more interesting in Physics 2 when you learn about electricity and magnetism, and I think Physics 2 also uses it for optics, for calculating like the intensity of light, though I might be mixing that up with the college version of the course. I'm going to have to refresh on that. But yeah, power we'll probably just touch on very briefly because it's not given that much importance in AP Physics 1 to begin with. And yeah, so probably 3 sessions and we will be done with this chapter. Maybe 4 sessions, but most likely it'll be 3 sessions and then we'll be done. It's not a very difficult chapter. I mean, don't underestimate it. There are definitely some common mistakes that students make with this chapter. And I have some problems that will highlight those common mistakes. But otherwise, it's not too bad, especially if you really mastered kinematics and force, which both come into play. I was only half joking a few minutes ago when I said it's time to talk about force again. Kinematics and force are still involved in pretty much everything we're going to do for the rest of the course. So, sorry, but those topics are here to stay. Physics isn't one of those courses where you can learn each chapter separately. They all build on each other. So, let's talk about work and energy. Let's start with definitions. So, what is work? We've got, of course, the definition in words, and then we've got the mathematical definition. So let's start by defining work in words. Work is the transfer of energy. Work is the transfer of energy. And that raises a question. What is energy? Well, you won't believe this, but energy is the ability to do work. The ability to do work. Wait a minute. Isn't this some sort of circular definition going on between these two words? So you're telling me that work is the transfer of the ability to do work, and energy is the ability to transfer energy? Well, actually, yes. It's not just some sort of conspiracy created by physics professors to keep themselves employed in jobs that they don't actually need to be doing. It actually makes sense when you think about it. If you have energy, then you have the ability to transfer that energy to something else. If one object has energy, it can transfer that energy to another object. And if it has no energy, well, then it can't do that. And if something is transferring energy to an object, then that something must have energy to transfer. It must have the ability to transfer energy. So it does make sense if you sit down and think about it for a couple minutes. It does actually make sense. So that is the verbal definition of work and energy. Let's talk about the mathematical definition. You might remember from, I think it was like the very first video when I was introducing just the basics of vectors versus scalars, you might remember something called the dot product or scalar product. And you might remember as an example, I gave the equation for work. Work is represented with a capital W, and the formula for it is force dot displacement, which I'll write it as delta x here, but of course it depends on the direction of the actual displacement. It could be a delta y or a delta s or delta r or whatever you like to call it. But work is the dot product of two vectors, force and displacement. And the dot product of two vectors has a magnitude equal to the magnitude of the first vector times the magnitude of the second vector, that's what these absolute value bars mean, times the cosine of the angle between them. And this is the version of the equation that most people will see. In fact, some people, I don't like this, but some people will write this as force times distance times cosine of theta. I don't like this because it's not distance, it's displacement. It's specifically displacement. So I have an issue with this, but this might be what's familiar to you if you're doing this in school. This might be the equation that your teacher wrote on the board. People will argue that, oh, d here isn't supposed to be distance, d is displacement, but we use d for distance, so that's kind of confusing. So yeah, I don't like it. But yeah, there's your equation. Force times displacement times cosine theta. I will just usually write f delta x or delta s or whatever, cosine theta without the arrows, so that we know that we're just taking the magnitudes. And yeah, if you're just taking the magnitude of one vector times the magnitude of another vector times, well, cosines are unitless, then what you are left with is a scalar. So yes, this makes sense. A scalar is equal to the dot product of two vectors. That's why the dot product is also called the scalar product. It's because you multiply two vectors and get a scalar out of them. You're just multiplying their magnitudes and the cosine of the angle between them, between their directions. So let's take a look at that theta and see what we mean by it. So suppose that I have a person over here who pushes on a box and this box moves by this much. and they apply a force in the following direction. Let's say they apply a force in that direction. Let's say they push at an upward angle, forward and upward. So that's their force applied. Okay, you would take the magnitude of the force multiplied by the magnitude of this displacement multiplied by the cosine of the angle between. So to get the angle between, what you would want to do is draw the two vectors tail to tail this time. And then there's your delta x. And you would want to find this angle. This angle would be the theta that you have to take the cosine of. Okay, pretty simple when your displacement is along the floor, which is why a lot of students will start making a certain mistake when doing these problems. They'll just assume that it's the angle that the force makes with the horizontal direction. But that's only true if the displacement is in a horizontal direction. What if the displacement is not in a horizontal direction? I'm going to have an example of that later, but basically if you have something like a ramp and you have a box on the ramp and the box is being pushed up the ramp, down the ramp, at whatever angle, doesn't matter. Let's say, for example, that the box is being pushed like this, not straight along the ramp, but something like that. And then here is the angle of the incline. A lot of students will use this theta, the angle of the incline, and plug that into their work equation. That's wrong. That's wrong. Where's the direction of the displacement of this thing? This thing is either going to move down the incline or up the incline. Let's say it moves up the incline like this. So if you know the angle that the force applied makes with the horizontal, if you know, I guess I'll do it in pink, if you know this angle, that's not the right angle either. That is also not the correct angle. This over here, also not the correct angle. What you need is to connect them tail to tail. So let me draw a parallel copy of this displacement vector, which I guess I'll call delta S. Let me draw a parallel copy of it there. And right here, this little thing over here, this is the angle that you would want in your work equation. The angle between the directions of the force applied and the displacement. As for the why and how of it, let's discuss. Let's suppose that we look at some simpler scenarios. Let's take a look at pushing a box just completely horizontally. So force is in a horizontal direction and displacement is also in a horizontal direction. So you've got force this way and you've got displacement also that way. Okay, well, I think it just makes intuitive sense here. I think most of you will easily be convinced without proof that when my force is in the direction that the object is being pushed, that would be the maximum energy transfer. That would lead to the maximum possible transfer of energy, because all of my force is going towards moving this box in the direction that it's moving. None of it is going towards, for example, fighting against the force of gravity. Over here, this force applied, part of it is just opposing gravity, while only part of it is actually pushing the box horizontally. So just in terms of components, you can probably see how that would make sense. In fact, if you took the force times cosine theta, then you get force times cosine theta is simply the component of the force that actually is in the direction the object is being moved. Same thing here, actually. Force applied times cosine of this little angle that we would actually use as theta. I guess we would have to call it something else because theta is already taken here. I guess we can call it phi or alpha or whatever Greek symbol you like. Phi, alpha. Sometimes they also use beta and gamma. But whatever symbol you want to use for the actual angle. If you were to take the force times the cosine of that angle, you would get the component along, well, this parallel to the incline direction. So, yeah, if you think about it that way, if you think of the cosine as just taking the component of the force that's actually working towards pushing the object in the direction it's supposed to move, I guess you could make sense of it that way. Okay, what about another scenario where the object moves horizontally, but now the force acting on it is upward? I guess I should have called that applied force over there as well. Okay. What about a scenario like this? Now, some people might be bothered by this. How can the object move horizontally if the force acting on it is upwards? Shouldn't it be moving up? Well, what if the object was already sliding and you just pulled up on it a little bit? Or pushed up on it from below, as the case may be. In fact, there is a force pushing up on it even in that first scenario. It's the normal force, and you've got the force of gravity pushing down on it. Neither of those two forces are actually doing any work because neither of them are contributing in any way to this horizontal movement. They are not adding to it, and they are not taking away from it either. So yeah, it actually does make sense that when the force is perpendicular to the displacement, no work is being done, at least not by that force. Also, there doesn't even have to be a horizontal force to have a horizontal displacement. We have been over this in previous sessions. We talked about this in the previous chapter. The forces acting on an object only have to do with the acceleration of that object. They have no direct bearing on how the object is moving at any given time. An object could already be moving horizontally before any forces are applied to it, and then you apply a force to it, and maybe you apply enough force to cause it to start changing its velocity, or maybe you don't, and you're just going to end up with a net force of 0 anyway, and the object will just continue moving as if you aren't doing anything to it. That's totally possible. An object's motion is independent of the direction of the forces acting on it. The direction of an object's velocity does not have to match the directions of the forces acting on it, depending on how it was moving before the forces started acting on it. I guess I will also add the force of gravity there. So yeah, neither of these two forces are doing any work. If you plug them into the work equation, you'll find whether you're talking about this upward applied force or this force of gravity, whatever its magnitude is multiplied by whatever the displacement is, multiplied by the cosine of the angle between their directions. Between force applied and displacement, the angle is 90 degrees. Between force of gravity and displacement, the angle is 90 degrees. What's cosine of 90 degrees? If you don't know off the top of your head, you can put it in your calculator. Cosine of 90 degrees is 0. Cosine of 90 degrees is 0. So yeah, when the force is perpendicular to the displacement, no work is being done. And finally, we have the situation where, let's say, an object is already moving to the right, and I have a rope or, I don't know, some sort of harness or handle and I tug on this object while it's already moving to the right. What happens now? Let's say you achieve that much displacement. Let's say the box manages to move to the right while somebody is pulling on it to the left. And of course there's normal force and gravitational force, but we'll ignore them because we just proved they don't have an influence on the work. What happens in this scenario? Well, in this scenario, we get negative work. If something is already moving to the right and I pull on it to the left, even if it does continue moving to the right, it will slow down because of this leftward force. So what does that mean? Am I adding energy to it? Am I transferring energy to it or taking energy from it? I'm taking energy from it. I'm slowing it down. And this will tie into something we'll talk about later. But yeah, I'm taking energy from it. And if we look at the equation, force times displacement times cosine of the angle between their directions, if the displacement is to the right and the force is to the left, so here's one pen representing force to the left, here's another one representing displacement to the right. What's the angle between these two? 180 degrees, and if you put it into your calculator, cosine of 180 degrees is -1. So the work you get is the force times the displacement times -1 in a scenario like this. You get negative work. In fact, you will get negative work for any angle that's greater than 90 degrees and less than 180. What about greater than 180? Well, you're not going to have that because when trying to determine theta for this equation, you would just take the smallest angle between two forces. For example, right over here, this theta over here, I could just as easily have gone with this big angle over here, 360 minus theta. And actually, if you did use it, then if you plug it into your calculator, you still get the same result anyway. That being said, I would still try to use the smaller angle between my two vectors because later on we're going to do something else where it's actually going to matter that we pick the smaller of the two possible angles that we could plug in. For cosine, fortunately, it doesn't matter, but let's not get too comfortable with that. Let's try and focus on getting the smallest possible angle between our two vectors when calculating work. One of them will be less than 180, the other one will be more than 180. Pick the one that's, well, 180 or less is what I should say, not necessarily less than 180. Pick the angle that's between 0 and 180, not the one that's between 180 and 360. Okay. I think we can just do some examples now. So, oh, actually before that, I wanted to comment. So when you have multiple forces, as is the case actually in pretty much all of these, I just didn't draw all the forces. Force normal, force gravity. I guess over here there might also be a normal force depending on how much applied force there is. And over here there's a normal force and a gravitational force. And over here there's a normal force and a gravitational force straight down, which we could break into components if we wanted to. And possibly friction depending on the scenario. So in these scenarios where you have multiple forces acting on an object, you can do two different things to calculate total work. Work total. You can do two different things to calculate total work. One thing you could do is just calculate work for each force individually. So for example, for this one, I could do the work due to the normal force plus work due to the applied force plus work due to gravitational force, and then that would be my total work. So that's for this example over here specifically. So that's one thing you could do. The other thing you could do, actually, let me just expand on this. So this is going to be work done by the normal force, so that's going to be normal force times delta x times cosine of 90 plus work done by applied force is going to be applied force times delta x plus, or no, times rather, cosine of 0 degrees. Cosine of 0 degrees is equal to 1 plus force gravity times delta x times cosine of 90 degrees. So you could do this. Or another thing you can do, turns out that this works as well. What you could do instead is you could add up all the forces, calculate what the net force is going to be, and then take the magnitude of that times the magnitude of your displacement times the cosine of the angle between the direction of the displacement and the direction of the net force. So if these three forces added up to be some force that's, at an angle, I mean, in this case, normal force and gravitational force cancel out, and the net force is just the applied force. But if normal force and gravitational force didn't cancel, if for some reason that weren't the case, then you'd have to do some Pythagorean theorem and add them up, and you'd get some net force that's either at an upward angle or a downward angle, depending on whether the normal force or the gravitational force is greater. I would assume the gravitational force would be the greater one if they're not going to be equal, because I don't see how the normal force would, well, maybe if it was on an elevator that's accelerating up, the normal force would be greater. But anyway, you'd get some sort of net force that's at an angle, because you'd be left with some vertical force and some horizontal force. So you'd get some sort of two-dimensional force, something at an angle, and whatever that angle is, compare it to the direction of the displacement and use that for your theta. So yeah, two different ways to calculate total work. You could either sum the forces first and then multiply by displacement cosine theta, or you can calculate the work due to each force individually and add them that way. This method might be easier in cases where, summing the forces is quick and simple. Other times you might prefer this, even though it has more terms in it. What's nice about calculating work individually for each force is that work is a scalar, and when you want to add a bunch of scalars, you just add them, or subtract as the case may be, because we established earlier that negative work is a thing. So whether you're adding positives or negatives, you're adding all the same, and you don't have to worry about direction when doing it this way, whereas you do have to worry about the directions of the things you're adding when trying to calculate the net force to calculate total work this way. So just some things to keep in mind, and let me write a more general equation for total work up there. So work total is also equal to, I'm going to call it work due to force 1 plus work due to force 2 plus work due to force 3, etc. That would be the more general equation for total work on an object. One force might be doing positive work, another force might be doing no work, another force might be doing negative work, and you take the combined effect of all of that and see overall is energy being transferred to the object or taken from it. But yeah, let's go ahead and look at some examples. Let me see. So this is going to be from the course plan, linked in the description in case you're new here. If we scroll down to work, energy, and power, and if you scroll down all the way to the bottom over here, I'm going to be looking at the work basics, and then later today the plan is to look at this one as well. Solutions videos are right there in the parentheses if you need to see them. I'm probably not going to work out the whole thing, but let's go ahead and see what we can do. Okay. And of course, these have two forms. There's a form A and a form B, so if I do one of them, you can still practice with the other one and go into it blind, which is nice. So we've got in our first example, two people push on a box. The first person pushes to the right with a force of 18 newtons. The second person pushes to the left with a force of 12 newtons. During this time, the box slides 5 meters to the right. How much work was done on the box by each person? And part B, how much work was done on the box by the force of gravity? How much work was done on the box by the normal force for part C? Part D, what was the total work done on the box? Did the box gain energy or lose energy, and how do you know? Okay, let's go ahead and answer all of that. So let's switch back. How about we go with this color? Okay, so there are two forces acting on this box, and overall it moves to the right. I'm not going to draw the people because that'll make the drawing a bit too crowded. Let's just draw the two forces. So there's force applied 1, as I called it in the drawing, force applied 1. And there's force applied 2, force applied 2. And then the displacement of the object is to the right like this. So they said delta x was 5 meters, force applied 1 was, did they say 18? Yeah, 18 newtons. And force applied 2 was 12 newtons. And this wasn't shown in the original diagram, but we do also have to add the normal force. This object is touching a surface after all, and that surface will try to push away on it. And the gravitational force, because this is presumed to be happening on Earth. So, questions were, how much work was done on the box by each person is part A. Pretty easy. So part A, work done by person 1, work applied 1, is equal to force applied 1, which is 18 newtons, times the displacement, which is 5 meters, times the cosine of the angle between their directions. Well, applied force 1 is to the right, and displacement is to the right. The angle between right and right is 0. There's no difference in direction between the two. Okay, cosine of 0 is equal to 1. 18 times 5 is 90. 90 times 1 is equal to 90. And that is going to be in units of joules. The units for work and energy is the joule, named after James Joule, represented with a capital J. And I guess I should have commented on that earlier, but 1 joule is equal to, well, let's see, work in joules is equal to, what are the units of force? Well, that would be newtons times what are the units of displacement? Typically, that's meters. So 1 joule is 1 Newton meter, or you might remember from, for example, net force equals ma, you might remember that a Newton, that 1 Newton is equal to 1 mass is going to be in kilograms times acceleration is going to be in meters per second squared. You might remember that a Newton is a kilogram meter per second squared. So if I take kilogram meters per second squared times meters, then that will be in units of kilogram meters squared per second squared. This is going to be useful in giving us some confidence about a statement that'll be coming up later today. This will give us some confidence that that statement will actually be true. But for now, just hold on to that. Anyway, so work due to applied force 1 is going to be 90 joules. What about applied force 2? Work due to applied force 2 is going to be, well, it's 12 newtons in magnitude times displacement is 5 meters times cosine of, let's see, so displacement is to the right, force applied 2 is to the left. The angle between right and left, those are 180 degrees apart. That's cosine of 180 degrees. Cosine of 180, as I mentioned before, is -1. So we've got 12 times 5 times -1. 12 times 5 is 60, and 60 times -1 is -60 joules. So 90 joules of energy are being added to this object due to the first applied force, but 60 joules are being taken away. So that's what we can glean from part A. Part B was asking us how much work is done by the force of gravity, and part C is asking how much work is done by the normal force. So work due to gravity is going to be the force of gravity on this object. Uh-oh, we don't know its mass. Is that a problem? Nope, not a problem at all. We don't need to know the force of gravity here because what angle does the force of gravity make with the displacement? Gravity is down, displacement is to the right. Down and right are 90 degrees apart. Cosine of 90 degrees is 0. Cosine of 90 degrees is 0. So this is equal to 0. I do not need to know the mass of this object. The mass of the object has no effect on how much energy I transfer to it when pushing it over the course of 5 meters. No effect. And then part C was asking what's the work due to the normal force. I don't think you'll be surprised by this one either. If the normal force is meant to cancel with the gravitational force, then we don't know it either. But that's okay, because the angle between the normal force and the displacement is yet again 90 degrees. We get 0 joules of work due to normal force. And that's all the work due to all the forces acting on this object. There are no other forces to consider. So part D, what's the total work done on the box? What is the total work done on the box? For part D, work total, we can just add what we already have. 90 plus -60 plus 0 plus 0. 90 plus -60 plus 0 plus 0. And that's a total work of 30 joules. Overall, 30 joules of energy have been transferred to this object. And then what was the follow-up question? Did the box gain energy or lose energy, and how do you know? Overall, this box gained energy, and we know because the total work is positive. We know that this object gained energy overall because the total work is positive. If it was negative, then of course we would conclude the opposite, that it lost energy. Okay, let's have a look at this second one, and let's see what we can do with it. So it says a box is placed on a smooth ramp, no friction in other words, as shown. The incline angle of the ramp is 27 degrees. Due to an applied force of 80 newtons at an angle of 42 degrees above the horizontal, it slides 7 meters up the incline. How much work is done by the applied force? And then part B, if the total work done on the box is 320 joules, how much work is done by the force of gravity? And then there's a challenge question, what is the mass of the box? The challenge question is, what is the mass of the box? Okay, let's go ahead and copy that over. And I think I want to start on a new page. So we have, this is what I warned about earlier. We've got the angle of the incline, which a lot of students will use as their angle for calculating work. Not good, not good. So this is theta incline, is what I called it in the diagram. And then we have an object over here. And then in all of these different colors, I'll try to use the same colors that I have over there. So we've got the force applied is at some sort of angle like that. So that's, whoops, force, not 5, F. Applied, and then that's just a dotted line representing the horizontal direction, and this, I guess I didn't leave enough room for it, but this is supposed to be a theta applied. I guess I will just arrow to it. That is theta applied, which we said was, well, let's see. So theta incline, we said it was 27 degrees, and theta applied, we said was 42 degrees. And then we have normal force, displacement, and force of gravity. So force of gravity drawn straight down like that. I bet this color doesn't look too different from the color I used to draw the ramp. And then normal force is just going to be like that. And finally, we've got the displacement, which is not part of our force diagram, but our displacement, delta S, parallel to the incline, is that. And then it said the displacement was 7 meters. Yep. Delta S equals 7 meters. And the applied force was 80 newtons. That's something I forgot to note. Okay, and the questions are, I guess I did end up solving this whole thing after all, but that's what the Form B is for. So first question is, how much work is done by the applied force? Part A, how much work is done by the applied force. Well, that's going to be the force applied times the displacement times cosine of what angle? Let's see. So the force applied is at an angle of 42 degrees above the horizontal. The displacement is at an angle of 27 degrees above. Did I say below? The force applied is at 42 degrees above horizontal, and the incline is at 27 degrees above horizontal, which would also be the direction of the displacement. The displacement is also directed 27 degrees above horizontal. So between 42 and 27, 42 minus 27 is 15. 42 minus 27. So we've got 80 times 7 meters times cosine of 15 degrees equals 80 times 7 times cosine of 15. Make sure your calculator is in degree mode. And I'm getting 540.918. I'll round that to 540.92. 540.92 joules. Okay, so that's part A. The applied force is adding 540.92 joules to this object. Part B says if the total work done on the box is 320 joules, how much work is done by the force of gravity? Part B says work total equals 320 joules. What is the work done by gravity? Wait a minute, the total work is less than the work done by the applied force? Are we bothered by this? We shouldn't be, because negative work is a thing. If you think about it, it does make sense that when you're pushing a box up an incline, gravity is working against the object. Gravity would be the thing that's slowing you down, taking energy away from you. So we haven't really talked about what type of energy work gives to an object yet, but I think you can guess just based on the descriptions we've been giving so far. We'll talk about it in more detail later, but the type of energy that an object gains or loses when work is done on it is kinetic energy, movement energy. So if more energy is gained than lost, the object will speed up. If more energy is lost than gained, it will slow down. And if it's already at rest, then the only thing it can do is gain energy. So yeah, we'll look at kinetic energy in more depth later. We will look at its formula and everything, and we will actually make a mathematical connection between work and kinetic energy. But for now, we expect the work done by gravity to be negative, so let's go ahead and use our total work equation. So work total is equal to work done by applied force plus work done by, what else is there? Normal force. No friction on this. We were told it's a smooth ramp. And all that's left then is just work done by gravity. Okay, well, normal force is in this direction, perpendicular to the incline. Displacement is parallel to the incline. That's a 90-degree angle between the two. So we already know work done by normal force is just going to have a cosine of 90 degrees in it. And cosine of 90 is 0, so that's gone. And we just solved for the work applied in the previous part. So 320 equals 540.92 plus work due to gravity. Subtract 540.92 on both sides. 320 minus 540 is negative 220 and minus 0.92, so it's negative 220.92 if I'm not mistaken. 320 minus 540.92. Yep, negative 220.92. Work done by gravity is equal to negative 220.92 joules. And I guess I should have circled that earlier as well. Okay, and that's parts A and B done. Now, there was a challenge question there. What is the mass of the box? We now have enough information to figure that out. We now know the work done by the force of gravity, so we can figure out what the force of gravity is from that, because we know the other pieces of the puzzle. We know, I guess I'll do it over here, work done by the force of gravity is equal to the force of gravity itself times the displacement, which is 7 meters, times cosine of the angle between the displacement and the gravity directions. Displacement is up the incline like that. Force of gravity is straight down, so what is this angle over here? What is that big angle? It's more than 90 degrees, that's for sure. As it should be, because it's supposed to come out negative. It better be between 90 and 180, because that's the only way that would work. Well, let's go ahead and do some geometry. So we have, I know this is, let's see. If I draw a dotted line there, I know there's 90 degrees in here between gravity and my horizontal line. And I also know that the displacement is along the incline, which is 27 degrees above horizontal. So we've got 27 here and 90 here. 27 plus 90 is 117 degrees. Of course, the other way you could figure this out is if you broke your force of gravity into components using the incline angle. You could have done force of gravity cosine of 27 will be equal to the component of gravity that counteracts the normal force and will just do no work. And then force of gravity sine 27 would be the component that's down the incline. And then you could do that. Force of gravity sine 27 times the displacement of 7 times cosine of, it would be 180 between the sine component of gravity and the displacement. And that should get you the same result. But anyway, work due to gravity, negative 220.92 equals force of gravity. I'm going to replace with mg, g being 9.8 of course, and then 7 and cosine of 117. I'm going to take all this and take negative 220.92 divided by all that, so negative 220.92 divided by, remember to use parentheses here, or use the fraction button like I do, divide by 9.8 times 7 times cosine of 117. Whoops, did I type 119? 117. And that's 7.09. So we get a mass of about 7.09 kilograms for this object. And there's the challenge question taken care of. All right, now what? I think we are ready to just talk about kinetic energy. Yeah. I think so. Why did I think that there was any chance that we wouldn't get this far? What was I thinking? Let's talk about kinetic energy. Before I lose my mind trying to figure out why on earth I thought we wouldn't, well, potentially wouldn't get this far. Let's talk about kinetic energy. So you've probably heard of kinetic energy in like your elementary school science class before. But kinetic energy, it's just the energy that an object has by virtue of its motion. I guess that's one definition you could give. Kinetic energy. The energy that an object has, the energy that an object has by virtue of its motion, by virtue of its motion. Motion. Oh, let me rewrite that. Motion. There's a new word. We just need to give it a definition. Moiten. The energy that an object has by virtue of its motion. Okay, well, how do we define motion? An object is moving if it has velocity or speed, and the greater the magnitude of that velocity, the greater that speed, the more kinetic energy that the object will have. And since energy is a scalar, the direction doesn't matter, so it really is all about magnitude. It really is all about the speed, regardless of the direction. So the formula for kinetic energy, some textbooks will call this capital K, some will call it KE. I prefer KE, but you can do whatever, KE or just K. The formula is 1/2 the mass of the object times its speed squared. So the heavier the object is, so if you have two objects both moving at the same speed, but one of them is bigger, one of them is heavier and has more mass, the more massive object would have to have more kinetic energy. More work would need to be done on that object in order to get it to that same speed as the smaller, lighter object. I shouldn't say smaller without lighter, because there are some objects that, despite being small, are heavier. You know, we could take like a golf ball versus a balloon. The golf ball would probably have more mass despite being smaller in size, so maybe size isn't the best thing to be alluding to. But anyway, kinetic energy equals 1/2 mv squared. Okay, so this was just given to us without proof. This was just given to us without proof. We can figure out the proof in a minute. We can figure out the connection soon enough, but let's give ourselves some intuition. Let's see if this actually makes sense. At the very least, let's make sure that we get the correct units from this. So kinetic energy, it's supposed to be in units of energy, so it's supposed to be in units of joules. So let's see. Well, the 1/2 doesn't really have any units to it, so I can ignore the 1/2. Mass has units of kilograms. And then speed squared is going to be in units of meters per second squared. So if we expand that, that's going to be kilograms times meters squared over seconds squared. Oh, wait a minute. That's exactly what we got before. 1 joule is equal to 1 kilogram meter squared per second squared. So at least in terms of units, so far it checks out. So far it checks out in terms of the units. The 1/2, though, seems to be out of nowhere. So where is that coming from? Well, it comes from force and it comes from kinematics. Let's put force and kinematics together. So earlier we said that the total work, one way to calculate it is to take the net force multiplied by the displacement multiplied by the cosine of the angle. So we're going to rely on that. Also, during this problem over here, we mentioned that the specific type of energy that's being added to or taken away from an object when work is being done on it is kinetic energy. This is what's called the work-kinetic energy theorem. Work-kinetic energy theorem. Theorem. Work-kinetic energy theorem. Or sometimes people just call it the work-energy theorem because it's a mouthful when you keep the word kinetic in there. But I like to keep the word kinetic in there because it reminds you what is supposed to go into the equation. The work-kinetic energy theorem tells us that the total work done on an object is equal to the change in its kinetic energy, delta Ke. That is, it's equal to its kinetic energy final minus its kinetic energy initial, which we can expand further into 1/2 of its mass times its speed final squared minus 1/2 of its mass times its speed initial squared. And of course, if you are dealing with an object whose mass is changing, then I guess you would call this mass final and mass initial over here, but those kinds of situations are rare. We're not really going to deal with that in Physics 1. Maybe in Physics C, you might, on rare occasion, have to deal with one if they want to throw a calculus-based question at you. They might give you something like a rocket ship and ask you to take into account the fact that fuel is being ejected from the back of the rocket and the mass of that fuel as it's being consumed is subtracted from the total mass of the rocket as it propels itself through outer space. But we're going to assume for most cases the very reasonable assumption that the mass is going to be constant, so there's no need for a mass final and a mass initial here. So yeah, that's the work-kinetic energy theorem. Tells us that the total work is equal to the change in kinetic energy, which, using our definition of kinetic energy, is 1/2 mv final squared minus 1/2 mv initial squared. But this still relies on our definition of kinetic energy here, so how on earth are we going to go about proving this? Well, if we do work total, whoops, that's a little bit better. If we do work total is equal to the net force on an object times the displacement times the cosine of the angle, then we know that net force on an object is equal to its mass times its acceleration. So total work is equal to change in kinetic energy by the work energy theorem, and net force is equal to ma by Newton's second law. I was about to say third law. That would have been wrong. We know that net force is equal to mass times acceleration by Newton's second law. We'll say that displacement times cosine theta Let's say that that is, for the sake of simplicity, let's say that delta S cosine theta is delta x. Let's say that your object is moving horizontally for the sake of example. It doesn't really matter. Let's try and give an illustration. Let's say here's an object, and let's say here's a random direction for its displacement. Let's say that's delta S, and let's say there's a bunch of forces on it. We add them up, and we end up with, let's say, the net force is in this direction. Let's say that net force is in that direction. And then I guess our angle between displacement and net force would be, let's see, displacement is that way, net force is that way, so the angle between them would be this over here. And then we could do delta S cosine theta or net force cosine theta. It doesn't really matter which one, but let's say we took net force cosine theta and we got this for net force cosine theta, the component of the net force that's parallel to the displacement. Okay, so that net force cosine theta is going to be equal to the mass of the object times the acceleration of the object in that delta S direction. So it's going to be equal to the mass of the object times its acceleration in that delta S direction. So that's your cosine theta basically accounted for. Let's say, better example, the one that I would rather go with is, let's say you have your delta S is just completely horizontal. I should have drawn this in the first place, but let's say your delta S is this way, and then your net force is whatever direction it is, let's say that way. And your net, and I guess this would be your theta, and then your net force cosine theta is like that. So that's your net force cosine theta. Then in that case, your delta S is just going to be a delta x, and your net force cosine theta, that's going to be your m times a in the x direction. That's basically what I'm trying to say here. So I will rewrite this and say change in kinetic energy equals mass times acceleration in the x direction for my specific scenario times delta x, and then that takes care of the cosine theta. Okay, well, acceleration in x times delta x. You might remember from kinematics what that is equal to. Acceleration times delta x. Which equation of kinematics involves a multiplication between acceleration and displacement? That would be the third equation. V final squared equals V initial squared plus 2 acceleration in x delta x. Subtract V initial squared on both sides, and I think some of you are already seeing where this is going. And now divide by 2, or in other words, multiply the whole equation by 1/2, and we have 1/2 V final squared minus V initial squared, at least in the x direction, equals acceleration in x times delta x. And if I go ahead and make this replacement, then change in kinetic energy is equal to mass times 1/2 v final squared minus v initial squared equals, I'll move the 1/2 out, so 1/2 m v final squared minus v initial squared. Oh, and distribute the 1/2 m equals 1/2 m v final squared minus 1/2 m v initial squared. Would you look at that? It's exactly what we were supposed to get. So yeah, that's where the 1/2 comes from. What about the y direction? Well, or not. Yeah, what about the y direction? What about the component of the net force that's vertical? I guess, actually, let me think. What would happen if we took that into account? Because if we're saying that the net force is in this random direction, then that means that the vertical forces are not balanced out. So there would actually be some acceleration in the vertical direction as well. I think I want to do this actually. Okay, so we've already done what I set out to do, but this is just extra, so don't get too much of a headache over this. But what if I took the other part of the net force? I guess it would be net force sine theta. Net force sine theta is equal to mass times acceleration in the y direction. And then, well, actually, hold on. Okay, I see what the problem is. So, if this really were the case, if there really was an acceleration in the y direction over here, then the displacement wouldn't be completely to the right like this. The object would actually have to move on some sort of upside down parabolic path. It would have to start curving upward. Okay, so yeah, we don't need to consider this. Okay, the example scenario I gave both here and here are not entirely realistic. If we're specifically working with an object that's moving in a straight line, then we don't actually have to worry about a net force that's not in the same direction as the displacement. Although, if the net force wasn't in the exact same direction as the displacement, it should still work out because, let me see, if I were to pursue this, if I were to entertain this for a second, if your delta S actually contained both a delta X and a delta Y, then this would be mass times acceleration in Y is equal to, well, we already said that acceleration in X times delta X equals 1/2 v final squared minus v initial squared in the X direction. So I can do something similar for the Y direction. So if I were to do change in kinetic energy equals mass acceleration in Y times delta Y by some similar reasoning, then I would have change in kinetic energy is equal to, I guess, change in kinetic energy in the Y direction. This is implying that energy has X and Y components, which I don't like because energy is a scalar. It doesn't have components per se, but let's entertain this idea for a minute. This would give me mass times AY delta Y is just going to be 1/2 V final squared minus 1/2 V initial squared. And then that equals 1/2 mv final squared minus 1/2 mv initial squared in the y direction. So I guess I'll put a comma y on these. So if I did quote unquote x components here and y components here of the kinetic energy, I'm not actually looking at components of energy. Actually, the kinetic energy, if this was your kinetic energy x and this is your kinetic energy y, I would say kinetic energy x plus kinetic energy y is your total kinetic energy change, is equal to 1/2 m v final y squared minus 1/2 m v final x squared plus, wait, no, what did I do? No, this is, I messed this up, hold on. No, if I were to add the kinetic energies in the x and y directions, if I were to calculate the kinetic energies separately for these two, which again is kind of nonsense, but let's entertain the idea for a second. Then let's see, delta k E in the x direction is 1/2 m v x final squared minus 1/2 m v x initial squared plus 1/2 m v y final squared minus 1/2 m v y initial squared. Okay, I can, if I add 1/2 m v x final squared to 1/2 m v y final squared, what is that? That's 1/2 m, and then in parentheses vx final squared plus vy final squared. That's going to be 1/2 m vx final squared plus vy final squared minus 1/2 m, and then do the same thing for the initials, for vx initial squared and vy initial squared. Vx initial squared plus vy initial squared. What's this? Vx final squared plus vy final squared. What's that? What's that? That is just the overall two-dimensional speed. That is just the overall speed. That's going to be, if I were to draw, if I have some, if this is my v final and it's got components, vx final and vy final, then this is just me doing Pythagorean theorem on them. Vx final squared plus vy final squared is v final squared, the full two-dimensional v final. Same thing over here. So this is actually, let me switch colors. This would actually be, I guess I'll continue it over here. This is quite the detour, but I think it's a worthwhile one. So this would actually be equal to 1/2 m, and then this is just v proper final squared, the whole two-dimensional v final squared, minus 1/2 m times vx initial squared plus vy initial squared is just the whole two-dimensional v initial squared. Again, by the same logic, this is just doing Pythagorean theorem to put the x and y components of v initial back together again. So your delta kinetic energy total between x and y, your total change in kinetic energy, does in fact not depend on the directions of the components. So yeah, I guess this is more of a full proof. I was relying on a simplifying assumption here, but I guess we don't actually need it. I'm going to have to look at this again and see if I can present it more cleanly in the future, but hopefully this has given you guys some insight. What I definitely don't want to take away from this is we don't want to treat kinetic energy as having components. That is not what's going on here. It's just that we happened to define two kinetic energies in terms of two different velocities, x velocities and y velocities. It's not the kinetic energy itself that has components because it's a scalar. It's just that the velocities that we were using to calculate them had components. So in this instance, it worked out. But I don't want anybody thinking that they can just, start with an object that has kinetic energy in some direction, quote unquote, and then decompose it into components willy-nilly however they want. Let's not do that. That's the wrong lesson to take away from this. The correct lesson to take away from this is that if the net force on an object is different from the direction of the displacement, then the displacement can't possibly be in a constant direction. The object has to move in some sort of curved path. Otherwise, there's something wrong about our net force. But yeah, there you go. So that's, I guess, what's the word I'm looking for? That gives you some confidence that all of this stuff is internally consistent. The work-kinetic energy theorem, the definition of kinetic energy, and I guess also the definition of work. Okay. I think with this, we can go ahead and look at a couple of example problems to wrap up. So, where do I want to look first? Well, we did say earlier that I wanted to do the kinetic energy and work energy theorem PDF from the course plan, so you can go ahead and open that. Let me show you real quick. That would be, if you open work, energy, and power, it will be right here. And it's going to look like this. And again, it has two forms, Form A and Form B. Let's take a look at Form A, and you can do Form B as an exercise. I might not even fully solve Form A, but I guess we'll have to see what's in it first before we make that decision. So it says a 5.4 kilogram box is kicked, causing it to go up a smooth, that is frictionless, 40-degree incline with an initial speed of 8.5 meters per second. Part A, how far does it travel up the incline before coming to a stop? Part B, how much work is done by gravity during this process? And Part C, how fast is the object moving at the halfway point between the bottom of the incline and the point where it comes to a stop? And then the challenge question, if the incline is rough and a kinetic friction force of 12.7 newtons acts on the box during its motion, what are the new answers to parts A, B, and C? Okay, I think I will leave the the friction part of it, the challenge part of it, as an exercise for you, but let's have a look at the basic question. So 5.4 kilogram box, initially at 8.5 meters per second. Let us have a look. I don't think I've used you at all today. So there's our incline. Box gets kicked. How much was the box? 5.4 kilograms. I suppose the mass is going to matter here. 5.4 kilograms. And it's a 40-degree incline. That's the angle of the incline, not to be confused with the angle that should be used for calculating work. Be very careful about that. I know I've warned about that, 3-4 times now, but it's just a common mistake. I see it all the time. V initial, we were told, is 8.5 meters per second, and we actually know what V final is going to be as well. Because we said this object is kicked up an incline and it's supposed to come to rest at some point. It's going to climb up and up and up and slow down, and eventually it's going to momentarily stop before sliding back down. But during that stopping point, V final is equal to 0. And the question was, how far does it travel up the incline before coming to a stop? What is this delta S? You could solve this using force. There is nothing stopping you from doing that. You could draw the force diagram, and I mean, we're going to have to draw the force diagram anyway. You could draw the force diagram, break your gravitational force into components, divide by mass to get your acceleration, and then you'd have V initial, V final, and acceleration, and the acceleration is going to be parallel to the incline, so you could treat this like a linear motion problem and solve it with force and kinematics, and that works. Oftentimes, once you get into the later parts of Physics 1, you're going to see a lot of problems that can be solved in more than one way. And you're just going to have to gain experience and practice and figure out which way works best for which scenarios. Sometimes it's going to be a trade-off between a number of steps and accuracy, and sometimes it's going to be a trade-off between accuracy and efficiency, and sometimes you won't have a choice just because of the information that you have to work with. Sometimes you're going to have too many unknowns to the point where it might still technically be doable, but way more complicated using one method over another. And a lot of times the easiest method tends to be the energy method. At least that's the pattern I've noticed, but again, you just develop a sense for it with experience. So when you see problems for this chapter, try to resist the temptation to use, well, I don't want to say resist the temptation to use older methods. What I would say is try to use the newer methods first, and then I would encourage you to afterwards use older methods and then just compare them and see what's working better. Anyway, we need to figure out the displacement of this thing. So force of gravity is acting straight down on this thing, and normal force is acting perpendicular to the incline. And there's no friction, at least until we get to the challenge question. We've got force of gravity straight down like that. And we've got displacement in that direction. So if we were using force methods, we would break this force of gravity into components and work with it that way. But using energy methods, we don't have to do that. Using energy methods, I would just say that work total equals change in kinetic energy. And work total, in this case, is the work done by the normal force plus the work done by the gravitational force, equals 1/2 m v final squared minus 1/2 m v initial squared. Work done by normal force, well, the normal force is perpendicular to the displacement. So it'll be normal force times displacement times cosine of 90 degrees. That's a 0. Work done by gravity. So displacement is that way, gravity is straight down. So we can do some geometry here. So straight down versus that right there. Force of gravity makes a 90-degree angle with the horizontal, and the displacement is making a 40-degree angle with the horizontal above. So 40 plus 90, the total angle between the two, 90 plus 40, is 130 degrees. I probably should have done that in a different color because this looks very sloppy. In fact, you know what? Let's do that. Let me write over it. Yeah, there we go. That's a little bit better. I hope. Did I? Oh, dropped it. Okay, so now we've got work done by gravity is force of gravity, mg. So, what was it? 5.4 kilograms, 5.4 times 9.8. That's force done by gravity, times the displacement, which we don't know yet, times cosine of 130 degrees. That's the work done by gravity. Force of gravity, displacement, cosine, equals 1/2 times 5.4 times v final squared, well, that's 0, minus 1/2 5.4 times v initial squared, which was 8.5 squared. It looks like we don't actually need to know the mass. It looks like we did not need to know the mass here because I can just divide everything by 5.4. I can divide the whole equation by 5.4. We're probably still going to need it for another part though. And well, this whole thing is 0, so that's out. So 9.8 cosine 130 is equal to negative 1/2 of 8.5 squared. 9.8 delta s cosine 130 equals negative 1/2 times 8.5 squared. Divide by cosine 130 and divide by 9.8, and delta s will be, let's see, negative 1/2 times 8.5 squared divided by 9.8 and also divided by cosine of 130. I'm getting 5.73, about 5.73. Delta S is about 5.73 meters, give or take. And it should be positive. Cosine 130 should be a negative, so the negatives on both sides of the equation should cancel out, right? 130 is between 90 and 180, but also force of gravity is supposed to take energy away from an object that's trying to move up an incline. You're moving against gravity. Gravity is going to slow you down. In fact, if it weren't for gravity slowing it down, it would never come to a stop in the first place. So yeah, that's what 3 different ways you know that the work done by gravity is negative. And that's part A. Part B, how much work is done by gravity during this process? Now we actually need the 5.4. So, actually, yeah, you need the 5.4. So you could either go back here and do 5.4 times 9.8 times delta S times cosine 130, or you could do negative 1/2 of 5.4 times 8.5 squared. I would rather use this because this relies on plugging in the delta S we just calculated. What if you made a mistake when calculating this? Or what if you have rounding errors that become even bigger rounding errors the more and more you reuse this? It's safer to use this. You're probably not going to lose any points if you did use this and just plug it in here, but you know, just risk management. It'll matter more when and if you end up working for NASA, but I guess as far as the AP exam is concerned, you don't need to worry that much about it. It's just good to adopt the mindset early. It's good to be able to spot these things. Okay, so I'm going to do work done by gravity is equal to negative 1/2 of 5.4 times 8.5 squared. This is why we needed the mass given. We did not need it for part A, but we do need it for part B. So negative 0.5 times 5.4 times 8.5 squared is negative 195.075. Negative 195.075 joules. And that's part B. And part C, how fast is the box moving at the halfway point between the bottom of the incline and the point where it comes to a stop? This sounds like a trivial question, but a lot of students will jump to conclusions about this one, and they'll say, well, obviously if it's at the halfway point, it should be at half of the speed, right? Wrong. Wrong. If it was the halfway point in terms of time under a constant acceleration, then yeah, that would be the case. It would just be halfway between 0 and 8.5. It would be what, 4.25? But this is the halfway point in terms of position, which is not the same thing. I would hope you remember this from kinematics because we did talk about this before. How fast is the box moving at the halfway point, and then in parentheses, between the bottom of the incline and the point where it comes to a stop? That stuff in the parentheses is telling you it's the halfway point in terms of position, not in terms of time. How fast is it moving at the half displacement point? Well, for that, we just use the same thing. Total work equals change in kinetic energy. So total work is just work done by gravity because normal force contributes nothing to the total and there are no other forces here. So that's going to be 5.4 times 9.8 for force of gravity times the displacement is now half what we calculated earlier, so we have to use this, even though it's a calculated result. 5.73 divided by 2. 5.73 over 2. 2.865. So displacement, I will use 2.865 times cosine of 130, as we established earlier, equals 1/2 m, I guess, oh, wait a minute, the mass is going to cancel out. Okay, this is going to be nice. I'll keep it as m, and then that's another m, and then v final squared this time. I guess I'll call it v half squared since it's at the halfway point, minus 1/2 m v initial squared, v initial being 8.5. Okay, the m's cancel out, the 5.4 cancels out everywhere, and I'm left with, this is not 0 anymore, It's something between 0 and 8.5, but it's not 0. Is it going to be closer to the 0 or closer to the 8.5? Actually, I'm not sure. Let me see. If I were to make that prediction, if I had to make that prediction, well, it's moving faster in the first half. So it gets to that halfway point in less time than the time it takes to complete the second half of its trip to the point where it stops. And so in less time, there's less deceleration. So I'm going to say it's closer to its initial speed. I'm going to say it's closer to 8.5 than it is to 0. Here's hoping that my reasoning turns out to be correct. So just plug in the numbers, I guess. I can multiply everything by 2 to get rid of the fractions. So 2 times 9.8 is 19.6. And then 2.865. And cosine 130. And then that'll be v half squared minus 8.5 squared, and then just add the 8.5 squared to both sides. So 19.6 times 2.865 times cosine of 130 is negative 36.09. Okay, I believe that. And then add 8.5 squared to it, and that's positive 36.1549. Okay, and that's all supposed to equal this v half squared. So if I take the square root on both sides, I'll take the positive root because we're just looking for magnitude here. I get 6.0128. I'm going to round that to 6.01. So v half has a magnitude of about 6.01 meters per second, which is closer to 8.5 than it is to 0. So yeah, my prediction from earlier is correct, which is good. Making predictions like that, I know I've said it probably a dozen times by now, but making such predictions before you work out your problem can help you catch if there are some mistakes that you may have made, whether it was a mistake in your prediction or a mistake in your actual solution. But when your predictions and your solutions match, it's not a guarantee, but it gives you some confidence that you probably did things right. Okay. And then the challenge question was, if the incline is rough and a kinetic friction force of 12.7 newtons acts on the box during its motion, what are the new answers to parts A, B, and C? If you add friction to the mix, you will no longer be able to cancel the 5.4 for part A, but it doesn't really change by that much. You still use the same equation, work normal force plus work gravity plus work friction, and for the work friction you would just do 12.7 times the new unknown displacement, which I would expect to be smaller than 5.73. If you have friction working against you, you stop a lot sooner, so you don't get as far. So I would expect the new delta S to be less than 5.73, but yeah, plus work gravity plus work friction, which will be the 12.7 times whatever the new delta S will turn out to be, times cosine of the friction would be against the direction of motion, so it would be cosine of 180 degrees. But the rest I think you can do on your own, so I will leave that problem there. Did I drop the... Wait a minute, where did it go? Ah, there it is. Man, this thing, I'm probably going to have to glue it on. It's the little cap that covers the, what would you call it? The little screw for the arm of my chair. It's been falling out a lot lately, which I guess it's really more of an aesthetic thing, so it's not the most important thing to have, but I don't know. I'll probably just have to glue it on or something to make it stay put. Anyway, what did we have next? We had, right, this second problem. So a 32.6 kilogram box is sliding on a rough surface with a speed of 12.3 meters per second. Part A, what coefficient of friction is required to stop the box in 45 meters? We could do this using force and kinematics, just like with the previous problem. And doing it again with those concepts, just to check your work and see if you get the same results, maybe off by a couple decimal places due to how you round, is worthwhile. But today, we're just going to focus on doing this using energy methods. So 32.6 kilogram box sliding on a rough surface with a speed of 12.3 meters per second. What coefficient of kinetic friction is required to stop the box in 45 meters? Part B, a person notices that there is a lake that is 30 meters ahead of the box. Assuming that the coefficient of friction is the same as what was calculated in part A, how much force would the person have to apply to the box to bring it to a stop before it falls into the lake? And then part C, if the person from part B decided to push with the exact same force but in the opposite direction, how fast would the box be moving by the time it reaches the lake? So those are our three scenarios to take into account. I think I will do just parts A and B. And then we'll probably just call it a day there, because I've got other work to do. What color do I actually want to use here? Let me think about this. I think green would stand out compared to the other colors we have on this page. So we'll copy the diagram. Did I switch cameras? Yes, I did. Or not switch cameras, switch scenes, but you know what I mean. And then there is a lake. I guess I will draw that in blue and make it wavy. And here's a box. It has some sort of initial velocity, so v initial in that direction. And there's a person standing there. I won't bother drawing the person. So first question was, mass is 32.6 kilograms. Let's note that. Mass, 32.6 kilograms. V initial is 12.3 meters per second. And for now, delta x is going to be, they said, what coefficient of friction is required to stop the box in 45 meters? So delta x is going to be 45 meters, at least for part A. At least for part A. Well, if I were to draw a force diagram, there would be normal force upward and gravitational force downward. And friction force is going to be opposite to the direction of motion, so it would be that way. Force, friction, kinetic is going to be to the left. And of course we know that force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. Also, I have no reason to believe that this object accelerates up or down, so I'm going to assume that the acceleration vertical is 0, which would mean that the net force vertical is 0. Net force, y, must be 0. Therefore, force is up, normal force, minus force is down, gravitational force has to be 0, so that tells me that the normal force is equal in magnitude to the gravitational force, so I can just go ahead and substitute this with mg. Force, friction, kinetic equals mu kinetic times mg for this problem. Okay, then from there we can do what? Total work equals change in kinetic energy. Total work is also either the work done by the net force or the sum of the work by each of the individual forces. Well, normal force will do 0 work because the displacement is going to be to the right while the normal force is straight up, 90-degree angle. Same thing for work done by gravity, that's going to be 0, so that only leaves the work done by the friction force. So if you were to do work normal plus work friction plus work gravity, normal force and gravitational force would cancel out. But also if you were to do it the other way, if you were to do net force times displacement times cosine theta, the net force, well, the vertical part is 0. We already said net force y is 0. And that just leaves net force x, which is the friction force. So either way, your total work is going to be force of friction times the displacement of 45 times cosine of, let's see, friction is to the left, displacement is to the right. Right and left differ by 180 degrees. And cosine of 180 is -1. And that equals change in kinetic energy. So we said this object is coming to rest. So that's going to be 1/2 the mass, 32.6, times v final squared is going to be 0 squared, minus 1/2 m v initial squared, minus 1/2 32.6 times 12.3 squared. 12.3 was our v initial as given in the problem. Okay, that's a 0, so we can just strike it out. And for the force of friction, we will replace it with mu mg. So that's going to be mu kinetic, which we don't know yet, m, which is 32.6, g, which is 9.8, and then, of course, the 45. Cosine 180 is just a -1, so I'll write that in. And then we've got -1/2 32.6 times 12.3 squared. Well, would you look at that? Just like in the previous problem, the mass cancels out, so we don't need the mass, and then the negatives cancel out, so we don't need that. Okay, solving for the coefficient of friction, divide by 9.8 and divide by 45, and let's see what we get. 1/2 times 12.3 squared, and then divided by 9.8, and then divide that by 45. And I'm getting 0.1715. Reasonable, that's what I typically expect to see when calculating friction coefficient. Friction coefficients, I expect them to be these small decimals, usually. So I'm going to say 0.1715. I'll do 4 decimals this time. Okay, and that's part A. What about part B? It says, a person notices that there is a lake that is 30 meters ahead of the box. So we don't have enough space for this box to travel 45 meters. With this coefficient of friction, it would need to travel 45 meters before coming to a stop, but it's going to reach the lake before then. So we're going to have to push on it to actually get it to stop before falling. So it says, assuming that the coefficient of friction is the same as what was calculated in part A, how much force would the person have to apply to the box to bring it to a stop before it falls into the lake? So now we've got one more force to add on. Now we have an applied force. Now we have force applied. And it's going to have to be applied to the left in order to stop this thing sooner. And you could probably, through intuition, guess that the applied force needs to be half as much as the friction force, because if the friction force... Wait, actually, hold on. If the friction is enough to stop it in 45 meters, then if you want it to stop in 2/3 as much distance, you would need to have 3/2 or 1.5 times as much force. Yeah. It should turn out that the applied force is going to be half as much as the friction force needed to bring this to a stop. So part B, I guess we'll do it over here. Only major change is now your work total also includes an applied force. The normal force and gravitational force are still going to be zeros, so they won't show up in your work total equation unless you want to explicitly write the zeros just to remind yourself that they're there. Which is actually not bad practice when you're first learning this stuff, but I don't want to insult your intelligence too much by doing that every single time, although I will probably still do that maybe like 2/3 of the time. I don't even know, but we'll see how it turns out. Anyway, force applied is also to the left while displacement is going to be to the right, so I'm going to get another cosine 180, which is just going to be a -1. I'm going to skip ahead and just call it -1 up front. So work total, we're going to have work applied plus work of friction equals change in kinetic energy is still going to be 1/2. In fact, I'm going to factor out the 1/2 m. 1/2 32.6 times 0 squared minus 12.3 squared. There. That way I don't have to write the 1/2 and the 32.6 twice. Okay, work applied and work friction, so we're going to have work applied is force applied, which we don't know yet, times the displacement now is 30 meters, right? For this problem, delta x is now 30 meters. And that's going to be a 30 in there, and then times cosine of 180, which is just -1, plus work due to friction. Now I know my friction coefficient is 0.1715, so 0.1715 times 9.8 times 32.6. I should have written the 32.6 first, but oh well. Multiplication is commutative, so it doesn't matter what order I write them in. But just for the sake of organization, I would try to keep things in order. And then displacement is 30, right? So coefficient mg, that's force. 30 is displacement, and then cosine of 180 is another negative 1. And then that's work applied plus work friction. And then we've got this. The 0 is just a 0, so we'll leave it out. And then we're left with negative 1/2 32.6 times 12.3 squared. Okay, so basically take all this, and I guess that's going to be a negative term, add it to the right, and then divide by negative 30, and that will give us our applied force. So negative 1/2 times 32.6 times 12.3 squared is negative 2466.027, so that's the right-hand side. And then plus 0.1715 times 9.8 times 32.6 times 30. That's negative 822.3024. And then, so that's this moved over to the right. So now that's going to be equal to negative 30 force applied. So divide by negative 30. And that's 27.41. 27.41. I get force applied equals 27.41 newtons of force. Is that within my predictions? What would the friction force have been? 0.1715 times 9.8 times 32.6. 0.1715 times 9.8 times 32.6. That looks like what I predicted. Friction force is about 54.8. 27.4 is exactly half of 54.8. So save for, obviously, there are going to be some rounding differences. But for the most part, it looks to be within my expectations. So that was part B. And then finally part C. I don't even know if I want to do this one, but it says if the person from part B decided to push with the exact same force, but in the opposite direction, how fast would the box be moving by the time it reaches the lake? So what if the person was actually a menace to society who saw this box sliding and was like, oh yeah, I'm gonna help this box along. Not only am I gonna sit by and do nothing and let the box fall into the lake, no, I'm gonna help this box fall into the lake. How fast will it be going by the time it reaches the lake? That is the question. So part C, I guess I will use this color for it. Part C. So displacement is 30 again. Displacement is 30 again. But this time the force applied is in this direction. This time force applied is in this direction and not this one. So we can remove that. Yeah, let me cross that out as well. So now we've got force applied is to the right. But otherwise its magnitude is the same as we calculated in the previous part. So the only thing that changes for the work applied is that since the direction has changed, now it's in the direction of the displacement. So instead of cosine of 180 giving us a negative 1, now it's a cosine of 0 giving us a positive 1. So it'll be total work is work applied plus work friction equals 1/2 of 32.6 times, this time it's not 0, this time it's an unknown v final squared minus 12.3 squared. And then work applied is 27 0.41 times displacement is 30 times cosine of 0 is 1 plus work due to friction is the same as it was before. All of that 0.1715 times 32.6 times 9.8, that's all the force, times the displacement is 30, times the cosine will give us -1, equals 1/2 32.6 V final squared minus 12.3 squared. Rather than distribute the 1/2 32.6, I think I'm going to divide it over to the other side. So let's see, half of 32.6 would be 16.3. So whatever this turns out to be, I'm going to divide by 16.3. So 27. Hold on, let me flip on these lights. I was wondering why the lighting felt different today. How did I go for 2 hours not realizing I didn't have the room lights on? That's how you know that I haven't had the most relaxing week. Anyway, 27.41 times 30 times 1, and then plus 0.1715 times 32.6 times 9.8 times 30 times -1, -821.4246, and then that divided by 16.3 divided by 16.3 is going to be -50.394. So -50.394 equals V final squared minus 12.3 squared. Add 12.3 squared to both sides. So 12.3 squared is 151.29. If I add this to the -50.394, what do we get? We got 100.896. We get 100.896 for V final squared. And then if I take the positive root, because we just need the magnitude, if I take positive square root, should get a little more than 10, 10.0447, I'll say 10.04. V final equals 10.04 meters per second. Now the question is, do I believe that? Does that actually make sense? If the friction is enough to stop it in 45 seconds, and the applied force is basically half the friction, so we've cut the friction in half, which would mean the friction is now enough to stop it in 90 meters instead of 45, something that should have been stopped in 90 meters that starts at 12.3 meters per second. By the time it travels a third of the distance that it takes to be stopped, well, in that first third, it should be a lot closer to its initial speed than it is to its final speed. We kind of reasoned through that earlier with this problem over here when we were making predictions about this 6.01. So yeah, I am inclined to believe it. I am inclined to believe this result. And of course, again, like I said in the beginning, you can redo this problem using force and kinematics and see if you get the same results, save for some differences due to rounding. But that will be it for today. That's where I'm going to have to stop. So for homework, for practice, what can I give you? Well, I mean, I did say this challenge question. I skipped this, so you might want to look at that, but also you can look at the Form B and try doing basically the same problems but with different numbers for both this exercise and the one from before. So that's one thing you can look at. You can also look in the book. Let's see. In the book, Work, Energy, and Energy Resources. Okay, so kinetic energy and work energy theorem is 7.2. So yeah, I would go up to 7.2 in conceptual questions and problems and exercises. Anything up to 7.2 should be fair game with what we have covered so far. And for next time, I guess we'll be looking at potential energy and conservation of it. And does this book not do... Oh, they don't have it in this chapter. Okay, they probably have it in a different chapter for... Wait. No, that chapter comes... They don't have elastic potential energy yet. That's something I'm going to want to cover, so that's something that's not in this book, unfortunately. At least not yet. They've probably reserved it for later when they get to... Where does this book even have its simple harmonic motion? Wait a minute, actually, where is it? Ah, there it is, chapter 16 is probably where they have it. Yeah, they probably stuffed it into chapter 16, but I'm going to be covering that in this chapter. I'm going to be covering elastic potential energy. Okay, it's good to know ahead of time that that peculiarity exists in the book. I mean, I'm pretty sure I have it stated in the course plan somewhere. No, actually, for the reading sections, I don't have it in there. Okay, I'm probably going to want to add that. I'm probably going to want to comb through chapter 16 over here and look into it. Although I guess my reasoning might have been that since I have the conservation of energy... No, wait. The conservation of energy demo video doesn't even go over that. Yeah, I don't know what I was thinking there. Not entirely sure. Well, I'll think about it and see what I want to do here. Maybe I'll keep it as it is, but probably I'm going to want to add some things here. Because also in this energy playlist, they should cover elastic potential energy in this playlist as well, if I'm not mistaken. I'll have to double check that before next stream. But that's all just for me to worry about. We'll cover it sooner or later. If we don't cover it sooner, then we'll cover it in the simple harmonic motion chapter. But I like to cover that stuff early so that simple harmonic motion is more of a breeze. So yeah, that will be for next time. And do I have any other problems to look at? Because I know I like to end these sessions with just a problem to think about. Let me open this book and see if I have a good one. Well, I guess this one is a classic. And by classic, I mean it's a problem that I give to students every single year. It says a mechanic pushes a 2,500 kilogram car from rest to a speed of v. So we've got a 2,500 kilogram car pushed from rest, v initial equals 0, v final equals, they just called it v. Doing 5,000 joules of work in the process. Work total equals 5,000 joules. During this time, the car moves 25 meters. Displacement delta x equals 25 meters. Neglecting friction between car and road, it says find v and find the horizontal force exerted on the car. So there's just some force applied here. Obviously there's gravity and normal force as well, so I'll leave completing the diagram to you. But yeah, shouldn't be too bad actually. Should be pretty easy. The one big thing for this chapter is it's easy when you're in the chapter and you know what you're supposed to be thinking, but a lot of students will, once they move on to later chapters and then they come back to this, like during review for the AP exam, and they stumble upon a work-energy theorem problem, they forget that the work-energy theorem exists. And they end up trying to solve what should be a really simple problem using combinations of force and kinematics, and they keep going around in circles and getting nowhere, or they end up with this needlessly convoluted solution, and it's all because they forget that the work-energy theorem exists. And I think that's probably in part due to, I don't notice a lot of teachers cover it in that much depth. I don't notice a lot of teachers giving it that much importance. So don't forget the work-energy theorem. Don't forget it's really about your understanding of work. It's really about your understanding of the concept of work. If you really drill it into your head that the energy being transferred when an object does work is kinetic energy, if you just remember that, if you remember an object gains energy when it speeds up, loses energy when it slows down, as long as you can really get your brain to hold on to that connection between energy and speed, you'll be good. If something is gaining energy, it is getting faster. If it's losing energy, it's getting slower. If you remember that, if you just let that get baked into your head as an intuitive idea, then you should be fine with remembering the work-kinetic energy theorem. Anyway, that is enough rambling from me. I hope you learned something valuable today. Take care, and until next time, class dismissed.